Hello everyone. In this particular video, we're going to start talking about epoxides. Epoxides are cyclic ethers. So we've previously talked about ethers which contain an oxygen as a functional group, an oxygen that's sandwiched between two carbon-containing groups. Now, what's peculiar or what's important about epoxides are these are cyclic ethers in a three-membered ring. So there is a three-membered ring where one of the atoms is an oxygen atom. So when you look at it, the oxygen is still sandwiched between two carbon atoms. It's connected to two carbon-containing groups. So that's an epoxide. And the epoxide carbons may have substituents on them. Okay. Now, this particular video is going to focus on the synthesis of epoxides. We're going to specifically talk about two of these syntheses, and both of them start from an alkene in some sense, okay? And I'll explain how. So the first one is the epoxidation of alkenes. So this is a direct synthesis from an alkene. You epoxidize an alkene, and the product is the epoxide. This reaction is done using peroxy acids. These are the reagents for making epoxides. So peroxy acid has a general formula of RCO3H. And so as you can notice, compared to a carboxylic acid, there is an extra oxygen over here. A good example of a peroxy acid, I guess the most commonly used reagent that you might find in organic chemistry textbooks is MCPBA, which is metachloroperoxybenzoic acid. So that's the structure of MCPBA. Now let's just look at the reaction itself. Very simple, very straightforward. If I start from an alkene, and I'm going to use a generic alkene here. So if I start from an alkene, and let's say we have R1, R2, R3, and R4, okay? And these R groups could be carbon-containing groups, they could be hydrogens, whatever that might be. There is some alkene. When you react this with a peroxy acid, RCO3H, now, if it is using MCPBA, the reaction is usually done in dichloromethane or chloroform as a solvent. Chloroform is a great solvent for doing these reactions. What happens is you synthesize the epoxide here. Now, once you synthesize the epoxide, important thing to remember here is that the stereochemistry is retained, okay, which means groups that were cis in the alkene, they remain cis, and groups that were trans in the alkene, they remain trans. Okay, so for this particular one, we can write the epoxide as something like this. So we have the oxygen, we've added the oxygen between those two carbon atoms, and on this molecule here, we can say R1 is on a wedge, which would mean that R3 is also on a wedge, to imply that they are on the same side. They are syn to each other, okay? And R2 and R4 are on a dash. And so again, that just implies that the epoxide, when this reaction happens, the stereochemistry of the alkene is retained, okay? And this is because the mechanism involves a concerted process. If you're interested in learning more about this reaction, please refer to a previous video that you can find in the alkene content folder that deals with the mechanism of the reaction and why we get this stereochemical outcome. Now, the second method of synthesizing an epoxide is from a halohydrin. But As I have noted here, a halohydrin is actually synthesized from an alkene. So this, in some sense, is also a synthesis that starts from an alkene. Okay, so if we start from an alkene, and if you do a halohydrin reaction on it, which involves the reaction with a halogen in water as a solvent. So I've used bromine as the example here. The reaction is done in water as a solvent. As you might recollect, the product here is the hydroxyl group on the more substituted carbon and the bromine group on the less substituted carbon. Okay, this is the halohydrin. So once you synthesize the halohydrin, so this is step one in some sense, first reaction. Now, if you react this halohydrin with a base, sodium hydroxide, let's say, what the base would do is it's going to react with this halohydrin, and although it may seem like, okay, there is a halogen over here and it's a primary alkyl halide, the hydroxide could act as a nucleophile and then do a substitution on it. But as we've seen a few times earlier, recollect that an acid-base reaction is always much faster than a substitution or an elimination kind of reaction, or any reactions that involve carbon atoms. So in this particular case, what happens is the base, instead of attacking that alpha carbon there, it would do an acid-base reaction. Okay. It reacts with that hydroxyl group in the molecule. And so we will get an intermediate, we'll get an intermediate where this oxygen is now negatively charged, and we have the Br over here. So that's going to be an intermediate that we will make. And this oxygen now, that's also a nucleophile, okay? And the sodium would be balancing the charge here. So the oxygen would go and attack this carbon. Now that attacks the alpha carbon of this alkyl halide, if we treat that as an alkyl halide. And simultaneously, the bromine gets kicked out. And so in the end, this would give us an epoxide as our final product. Okay, so the halohydrin, which is synthesized from an alkene, can also give you an epoxide when the halohydrin is treated with a base. So treating a halohydrin with a base is going to give us an epoxide, and this reaction would be done in steps. So we'll look at an example here. So let's say if I take an alkene, and we'll say that there is a methyl group here. Okay, if we start with an alkene like that, if we first react this alkene with Br2 and water, and then react the halohydrin that's formed with a base, it would furnish the epoxide intermediate here. So we will get the epoxide here. And if this epoxide is on the board, then the methyl group here would be on the dash here. And in this particular case, since we have a methyl group here, we are going to be creating a racemic mixture if we track the stereochemistry of the product. Okay. Now we can look at the mechanism in a little bit of a detail. Okay, not too much, but a little bit of a detail here for the mechanism. So once we do the initial halohydrin reaction, the halohydrin reaction is going to give us the intermediate where the hydroxyl group is going to be on the more substituted carbon, which is this carbon, and the bromine is going to be on the less substituted carbon. Now, something that we could not show here but can be seen clearly here is the anti-addition that happened, okay? So the hydroxyl and the bromine, they are anti to each other. So this is one possibility. And along with this, you will have its enantiomer, right? So you're going to make its enantiomer along with that. That would be the intermediate after the first step. And then when the reaction happens with base, we are converting that into the final product through that ion. So sodium hydroxide, when it reacts with this alcohol or the halohydrin, the hydroxyl group in the halohydrin, it will give us that nucleophile, the O minus, and that O minus is now going to give attack on the halogen or the alpha carbon here to kick out the halogen as a halide, and that would give us the product. So that's how we get to this product. So that's just a quick discussion of the two methods to synthesize epoxides. One is a direct epoxidation reaction using peroxy acids as reagents, and the second is from a halohydrin, which is an intermediate from an alkene. So you can convert an alkene into an epoxide through the intermediacy of a halohydrin. I hope everyone finds these videos helpful. Bye.